Okay, I haven't finished the marking on the midterm yet, so I'm aiming at next Monday. Today we'll talk about Lagrange Multiplier, and basically it's a continuation of the optimization problem, the mean and max. After we finish, if we got time, then I'll go over our midterm exam paper together, okay? So a few things I noticed when I was marking the midterm exam. Alright, so in the previous lecture, we have talked about is how do we find the mean or max of a certain function, right? When you're giving, let's say, a function like this, and we see the objective is what is the mean or max of this function, right? So that's for this kind of function. This is from previous lecture. For this kind of question, and oftentimes we call this is basically called unconstrained, okay, unconstrained problem. Okay. So what does that mean is basically you don't have any constraint on the x and y value. So x and y value can be anywhere, in the space. So then you try to find basically the mean and max. That's called unconstrained problem here, right? Yeah. So today we'll tackle is so-called constrained problem. Okay. And to tackle that problem, we're going to use an approach called the Lagrange multiplier. Okay. Yeah. So the topic is we're trying to find is we're still looking for this mean or max kind of problem, but we'll be looking at is this so-called constrained case. Okay. Yeah. So I'll talk about what exactly is a constraint and the meaning of the constraint in here. Okay. So very similar. So we have this so-called objective function. Okay. The objective function is basically what we call the original function. This is z equal to f of x, y. Okay. So I'm taking a function of two variables for example. You can use function of three variables or even multi-variables, no problem at all. Okay. So this is called objective function. And then the objective function basically is what's this function's mean or max, right? So that's the original problem. And then you have this constraint now, okay, constraint. Okay. So constraint essentially, now your x and y will not change arbitrarily. It's going to be constrained to a function. Okay, so this is the kind of a generic expression we call a constraint. So what this expression right here, g of x, y, anything you can put it here. For example, x squared plus y squared equal to 4. So that's a circle, right? Maybe basically the constraint could be a circle, for example. Okay. Okay. So that's a type of constraint. Or maybe it's a straight line, x plus y equal to 3, something like this. Right? So which means your x and y, well, you're still looking for mean and max of this function, but it's not anywhere in space. It's being constrained. In this case, it's where it's being constrained to this circle. In this case, it's being constrained along this straight line in here, right? Yeah. So that's basically what I mean in here. So in other words, if I explain this a little bit better, so let's just say you have a surface at here. Okay. So this is your z equal to f of x, y. Okay. Okay. So in the previous lecture, we were saying, okay, where's the mean and where's the max of this surface, right? And that's what we did. Remember what we did? We did a what? We did a first derivative test, and then we do a second derivative test. So first derivative test gives us the so-called stationary point or the critical points. Then you do the second derivative test to find what that critical point is. Is that a mean or max or saddle, right? Or not conclusive. Okay? So in this particular case, your x and y is constrained, maybe let's just say to this straight line here. So this is your constraint. Okay, this is your constraint here. So x and y will not go anywhere but changing along this, okay, along this straight line. Okay. So the question is, when you're changing your x and y, okay, along this straight line at here, okay, what will be the mean or max as the corresponding points changing along the surface, right? So that's essentially a different perspective regarding the mean and max. Okay, yeah. So we'll look at the specific example like this. Okay, next. So let me give you another example here. It's a very common example. Okay, another constraint problem like this. Let's just say you're going to design a fence. Okay, so you're updating the garden. Okay, so your garden, you need to install a fence for your garden. Okay, to enclose certain area. And you know your area, okay? So design a fence for, you know that your area of this garden, okay, your backyard is 1,200 square meters. Okay, that's pretty big. So, and now you're looking into this. What should we buy, and what will be the cost for the material we're buying at here? Okay, so I'm going to draw the fence out here. So basically, okay, we're designing, let's just suppose that we're designing a rectangular fence, okay, area. So the condition you know is for this side here, okay, suppose this is the side, okay, this is the side facing straight. And you want it to have a better material, okay, just to give a better appearance for your fence. For this side here, the cost, okay, is $50 per meter. Okay, so the red side is $50 per meter, and the other three sides, okay, the other three sides is, okay, is $30 per meter. Okay? Yeah. Okay. So now you have the knowledge. Now you go to Home Depot. You want to buy those material, and let's just say I'm going to denote this red side as L. Okay? I'm going to denote this length as W here, as a height, W. Okay? Yeah. So the question is, we want to minimize the cost for the fence we're building. Okay, we're minimizing the cost. So you're minimizing the cost. Basically, what you want to do is you need to come up with the function, right? Calculating the cost for the fence. Okay. So first step is, what's the cost, okay, for the fence based on the given condition? So what will be the cost for the fence here? L cost is $50 per meter. So this side cost is 50 times L, right? And this side is $30, and this side is also $30. So what will be the cost for the other three sides? 30 times W plus 30 times W plus 30 times L. Okay? So that will be the total cost for your fence. Okay? Yeah. And what we want is, we want to minimize the cost. So in this case, this is my objective function, right? This is my objective function. Okay? And my objective is to minimize this thing here. Okay? So it's a minimization problem. Okay? We want to minimize this cost. At the same time, remember the constraint. What's the constraint here? You have the constraint is the area is 1200 meter. So next one is constraint and here. Okay. So constraint, basically you're subject to a condition that W times L equal to 1200. Okay. Yeah. So altogether, right, this is basically the optimization problem you're looking at. Okay, it's a constraint problem. Okay. So you can simplify the first one a little bit here. So what would that be? 80L plus 60W, right? Yeah. Okay. So if I don't teach you anything about the Lagrange multiplier that we're going to do, when you look at this one here, right? Actually, if you're in high school, you can still solve this problem. Okay, you can still solve it. So how do we solve this problem then? And one of the approaches to do what? WL equal to 1200. So what you can try is this. So from here, you can extract, let's say, L equal to this. Is that okay, right? Yeah. And then you substitute this L into this cost function, right? So this is basically, over here, this is basically your f of x, y, right? This is basically this function right here, okay? So if I sub this L into here, then my cost will equal 80 times, and that guy is a pretty big number, and plus 60W, right? Plus 60W. Okay. Yeah. So now, if you look at this one here, okay, if you look at this, that basically becomes a function of a single variable now, right? Yeah. So actually, you can do one more step over here. You can do 80 times 1200, whatever that value will be, and then plus 60W squared over W, right? Over W. Okay. So your idea is basically you're trying to minimize this one. Your original is minimize the cost, then you're going to minimize is this one here. Okay, this. Okay. So how do I minimize this one? Exactly, right? You take the derivative with respect to W. Right. So basically partial, not partial. D over dW cost. Right. This function. And set it equal to 0, right? Set the 0. Solve for the W. Okay? Solve for W. Does that make sense? Right? So in this particular case, you're going to guarantee it's going to be a minimizing problem, but mathematically, the value that you get for the W, you need to do a second derivative test to see whether it's a mean value or maximum value, right? Yeah. Okay? So that's basically very typical substitution problem to solve this one here. So this is okay. This is okay basically meaning because now you only have two variables, right? Two variables. You know, think about that, the different scenario. What if my cost beside the L and W, and then probably plus my gas cost or some other things, right? So you will have another variable set here. So then, in that particular case, this approach generally we call a substitution approach, or to reducing, basically to reduction of this variable. That won't work very well anymore, particularly you have a multivariable, more than two variables. Okay? Yeah. So this is the reason we need a more generic approach here in terms of this constraint problem here. Okay? Yeah. So let me start this one. I'm still going to use this function two variable to illustrate the idea, Lagrange multiplier idea here. Okay. Yeah. So now I'm going to just kind of rewrite my two functions at here. Okay. Yeah. So let me draw something like what I did above there. So let's say I have a surface, okay? Yeah. Okay? Yeah. So we want to make use of what we have learned at here to come up with a very simple conclusion, okay? Yeah. So now suppose that this is my constraint. Okay? This is my constraint here. Okay? Okay. So let's go back, step back a little bit here. When you look at this constraint in here, okay, g of xy equal to c. Let's think of this one, okay, in terms of the contour curve. All right. So what I mean at it is this: if I don't let this one, if I say, okay, get rid of the c here, assuming this, assume you have a function maybe w equal to g of xy. Is that okay, right? You have a function like this. Okay? Yeah. And if you recall that when we're learning visualization of a function of two variables, and one way to visualize that is through what? Through the contour forms, right? Contour curve. And what is contour curve? Contour curve basically meaning you let w equal to a different value, constant values, right? So basically that's the case at here. So when you have a constraint like this, c could be 0, it could be anything. Okay? When you have a constraint like this, that's essentially we can consider this guy, okay, as a specific contour curve coming from this function. Okay? Yeah. As a contour curve. Okay? As a contour curve from where? From this w equal to g of xy. Okay? Does that make sense? Yeah. So I'm just drawing this one here. You know, sometimes we have a pretty beautiful contour curve, a cluster of circles, right? So let's just assume you have a contour curve like this. So now the constraint, you think of as contour curve, and your x, the change of x and y is going to be along this curve right here. So let's suppose you have a stickman here. So you're going to walk around this curve right here, right? I often use this for illustration. At the same time, you have another guy on the top, okay, which is on the surface z equal to f of x, y. Okay? Yeah. So as this bottom stickman is walking around the curve C, then the top one, the red one, is also going to change along the surface at here. Make sense? And guess what? The trajectory of the red guy will basically trace out, okay, I'm not sure what, will trace out a curve, right, along the surface given there, when this one is moving around here. Okay? Yeah. So, for the bottom guy here, when it's moving along the curve, and we often say, what direction is this guy moving, right? So in this particular case, if this is moving, let's say moving towards this direction, so at any instant, what shall we use to indicate the direction of the moving of this bottom one here? We can use what? Pardon me? Directional derivative is not a direction yet. I'm saying it's walking along the curve here. I can use what information from the curve to represent the direction? Tangent vector, exactly. So I can use this tangent vector here to represent the direction of moving. Okay? So this B, let's see, so B is moving, okay, in U hat direction, which is tangent vector, okay, for this curve here. Okay? So that's good, right? In a tangent vector, we can get that once you have the curve. Okay? So, you have u hat here is moving. This is your direction of changing, basically u hat, which is a tangent vector. Now in the previous lecture, we learned one fact. So this is the function w equal to g of x, y. And this is one particular contour curve coming out of here. So tell me, what is the relationship between the gradient vector of the function g and its contour curve? Do you remember that? You have the gradient vector del g at here. What is the relationship between this del g and the contour curve of g of x, y? What's the relationship between these two? Perpendicular. Okay? So, which means, actually I have a second one here from that lecture. This is perpendicular to the contour curve. Equivalently, we can see that this del g is perpendicular to what? To the u hat, right? To the tangent vector of that contour curve. Okay? So if I draw this out here, the del g, let's see, at this moment, the del g will be in this direction. Okay? Will be in this direction. If at this moment here, the del g might be this direction. Who knows? Maybe, right? There are two directions. Okay? But either way, the del g will be perpendicular to the u hat. Okay? Yeah. So that's number one fact. Okay? Number one fact. Following my logic here. Okay? It's very important. You don't lose any chain. If broken one chain, you won't understand the final conclusion here. So let's just say this is a fact number one. Okay? So now I'm going to talk about fact number two. Okay? Yeah. Fact number two is this now. So this bottom one is moving along the curve, and the top guy is going to have a change, right? So in other words, we learned directional derivative. So when you're walking here, there is a rate of a change for this particular one, for this Diekmann red one here. Okay, there's a rate of change, and we call that what? We call that directional derivative. Is that right? So basically, fact number two, coming from the directional derivative. So df over ds u hat. That's directional derivative. So just repeat this idea here. What's the directional derivative? Directional derivative is the rate of change of a function f when you are moving in the direction of u hat by a small distance or displacement ds at here. Okay? So what is the directional derivative formula? Which is what? Which is del f dot u hat, right? Del f dot u hat. Okay? So the second fact coming from this one here. Remember what we're looking for. What we're looking for is, as this one is moving along the constraint curve or the contour curve G here, what will be the mean or max location, okay, experienced by the red guy here, right? That's the objective, okay, objective. So if this guy happened to be at a minimum location at here, okay? If this guy happened to be a minimum location corresponding maybe to this location, right? So now you tell me, at this location, okay, at this location here, what will be the value of directional derivative then? Value of directional derivative. So you walk around here, so that guy is following, and at here, suppose that experience this mean point, at the trough. Okay? What will be the directional derivative for that at this point? 0, right? If I ask you a different question here, here's a curve. As you are changing along the x-axis direction, and then right at here, what will be the slope? 0, right? Same idea. Directional derivative will be 0. Along that curve traced out of the red guide, if it is a max or mean point. Make sense, right? So this is basically the second factor here. So df over ds equal to 0 if at x naught y naught location, and there is no change in f. There's no change in f. That makes sense? So maybe this is x naught, y naught. Who knows, right? But at that location, there's no change in df over ds. So that must be 0. Okay. So df over ds is 0. Then you're coming back to this directional derivative formula. If this is 0, what does that tell us between del f and u hat? Perpendicular. That makes sense? So slowly we're getting to there, okay? Fact number 1 is pretty general. Del g is perpendicular to u hat all the time. Okay? So as I draw it over here, always perpendicular. And the second fact is this, now it's a particular, not always, is maybe at a certain location basically, right? And you end up with this mean or max location, which basically means around that location there's not going to be any change in f, okay, very small rise. Then the slope, or now what we call in general, the directional derivative is 0. So, direction derivative is 0, basically dot product is 0. Dot product is 0 meaning this vector must be perpendicular to u hat. Okay? Yeah. So combining the two facts now. Okay, let's combine the two facts. Fact number 1 here, fact number 2 at here. Okay, so let's come back to this drawing here. Okay, come back to this drawing. Del G is perpendicular to U hat always. Okay, always. Suppose that this is a location of mean or max. If this is a location mean and a max, what fact did we just find out? The del F is perpendicular to U hat 2, right? So how do I draw the del F? You did assignments. So at this location, calculate the grading vector and draw the del F. So both del G and the del F, in this case, are in this xy plane here, right? They're all in xy plane. So you consider the geometry here. This guy is perpendicular to U hat. And del F is also perpendicular to U hat. So tell me, what would be the relationship between the vector del G and the vector del F? Geometric relationship. Parallel, right? So can you see that? So you have this guy perpendicular to this. Where's my del F? Maybe del F is here, right? Or maybe this way, who knows, right? Yeah, but it has to be perpendicular to U hat if that location is a mean or max. That make sense? Yeah. So in other words, after all this long-winded story, the conclusion is just one sentence. If this x naught, y naught location corresponds to a mean or max along the curve traced out by this red guide, then the del G and del F must be parallel. Okay? So, let me write it down in here. Now, this is not a very a generic expression, mathematical expression. So when you see two vectors are parallel to each other, mathematically, what would be a better way to express this in here? Scale difference. So I can use a scale to represent the relationship between these two vectors. So to facilitate the writing, as you can, I'm going to put a negative here, okay? Yeah. So actually it doesn't matter, but just to for the conventional writing. So I'm going to put a negative here. So they're only going to be a scale difference. They may be pointing to the right direction, the same direction, or maybe to the opposite direction, but they are only a scale difference. Okay? That's basically, that's it. Almost that's it. So the lambda here, this lambda is called Lagrange multiplier. Okay, Lagrange multiplier. So what this is good is, right, now we connected the function f, which is the original objective function, and this constraint function g, together using this relationship, right? Together using this relationship. Okay? Yeah. So this is basically enough now, but maybe I'll just extend this just slightly here, okay? Just extend the idea just slightly. Now, remember I said this is a contour curve, right? This is a contour curve. And maybe I should draw a better one here. So this is the contour curve at here. Okay. So let's relate. Okay. Let's use the same idea, contour curve. Okay. For this function. Okay. So this is a surface. You can also establish a contour plot for this surface. How do you do that? You basically slice that, right? You slice that using different z value. Okay. Yeah. So as we were saying, maybe this is, okay, maybe this, let's use this one here just for illustration. Maybe this x naught, okay, y naught is a mean or location, mean or max location. Okay, it's a mean max location. And as we just said here, at this location, your del g and del f will be parallel. Okay, will be parallel. Okay? So since del G and del F, I'm not sure. Maybe it's the same direction. Who knows, right? So that's basically going to be parallel. So now you think of this now, okay? We said del G is perpendicular to U hat because the gradient vector is perpendicular to contour plot. Same thing here. What about the del F? Del F must be also perpendicular to what? To its own contour plot. That makes sense? Right? So, the question may be asked is now, if I give you this point here, okay? If I give you this point, can you draw the contour plot given this location for this function, for this surface? You have a location right here. You have the surface. What would be a contour plot for this surface? Sure, it's just, but let's say in general here. How do you generate the contour plot or the function for the contour plot? So here what you do, given this location here, what's the z value? The z value at this location is what? Is that right? That's a z value. How do I generate the contour plot then? You slice, okay? You slice the surface with what value? With a plane z equal to z naught. Okay? So what's the contour plot now? The contour plot is f of x, y, control plot is to set the z to certain constant. In this particular case, the constant is, okay, see, this is the contour, okay, plot, okay, at x naught, y naught for function f of xy, okay, function xy. So if I draw it, it gotta be something in the xy plane, something like this at here, okay? Something like this at here. So I'm not gonna draw it yet because I need a factor here. Del G is perpendicular to this contour plot. What about del F? Del F must be perpendicular to this contour plot. Does that make sense? So del F is perpendicular to this one. Okay? It's perpendicular to this contour plot. And what point does this contour plot go through in xy plane? Which point does it go through? This contour plot goes through which point? Go to the same, yeah, x naught, y naught, right? Go through the same point here. So now the question here comes now. What would be the relationship given this relationship, what we just said here? So del G is perpendicular to this one, okay? To this one. And del F is perpendicular to this one. Now, how about these two contour plots? So between this and this, okay, between these two, what is the relationship at x naught, y naught location? Because both of them go through the point of the location x naught, y naught, right? Both of them go through the same point. And you have these two relationships. And you have this one. So tell me, what's the geometric relationship between the two curves at this location? You got two curves. Curves not parallel. Basically you got another curve going through this point. Not a multiplier. Think about it in terms of tangent vectoring, okay? When I say this is a tangent to this contour plot, it's same language as del G is perpendicular to what? To the tangent vector at the location U hat, right? So if I draw a line in here, so this del G is perpendicular to that line, tangent line. And del F is also perpendicular to this line. So how about the contour plot for the function f here? What's that going to be? This contour plot, these contours going to be, they don't intersect, they touch. Tangent, right? Tangent, okay? That's the word. So this and this tangent at this location, okay? You see the meaning behind this mean and map, the geometrical meaning basically, okay? For constraint problem here. So you will have the two contour plots tangent to each other, but only at that mean or max location though, alright? Yeah. Because at other locations, you can ask, what will be the relation between other, maybe at this location, you have another contour plot. So all you can say is probably the two contour plots will intersect each other, or maybe not even touch each other. Right? Yeah. But a special case is, if it's the mean and max, they will be tangent to each other. So essentially, okay, all I've been saying is, when we're looking for constraint optimization problem, you can state two sentences. Either one of them will be equivalent to the other. Number one is, if it's a mean or max location, this is checked. Number two is, this is checked. Okay? Yeah. That make sense? Yeah. Okay, so now we're ready to do some further digging in here. Okay? I guess the tangent convention is probably hard to be used to do any calculation. However, this one is quite handy. Okay, this one. So let's take a look at this one. What does this one give us then? From del F equal to this, let's see what can we derive. Okay, what can we derive? So del F is what? Fx, Fy. And del G is Gx, Gy. Okay? Yeah, Gx, Gy. If these two are the same, that means partial F over partial X equal to lambda X partial G over partial X. Or the other way writing is just move all of them to one side. Okay, that's the first equation you get, right? First equation. And the second equation, similarly, okay, you get this. Okay? So you got two equations, and you're going to solve. Okay, you're going to solve for possible values x and y and lambda. Okay, to find the mean or max location. But imagine this, right? You're going to have two equations, but how many variables? Actually, we're going to have x, y, and lambda, three variables, right? So it's not enough. So from here, you need another word, basically, which is what? The constraint. Don't forget the constraint here. So now you have three equations, three unknowns, so you will be able to solve for a set of values, x, y, lambda. Okay, that's basically, in terms of the mathematical formula for constraint optimization problem, mean and max, three equations. Okay, like this. Make sense? Yeah. So, better yet, okay, particularly if you are going to learn some further courses in control systems, in engineering optimization problem, you'll encounter the next formula quite a lot. So, one of the guys, which is called Lagrange, okay, basically coming from Lagrange Multiplier, he said is let's combine the three equations together. Okay, combine them. So this is what happens here. Okay, so we define another function. Okay, a so-called Lagrangian. Okay. We define a so-called Lagrangian here. And the Lagrangian is defined by this, using a capital L right here. Okay. So the Lagrangian essentially is defined like this. Okay. So he defined a new function based on the original objective function f of x, y, and sometimes we call it cost function, and the constraint g of x, y equal to c. Okay, so combine these two together, and with the Lagrange multiplier lambda here. So now the question is, the original basically finding mean or max problem becomes a new problem. The original mean and max subject to a certain constraint becomes a more simpler one. Becomes what would be the mean or max for the L and here, okay, for L. So if you look at the, I'll explain why it's equivalent working at here, okay? The first observation is, when you look at this Lagrangian here, and then when you're looking for the mean and max, what would be the difference between this problem and the problem that's stated at here? What would be the difference? This is a problem finding mean and max subject to constraint. But now, this one at here, is there a constraint at here now? There's no constraint anymore, right? So this has become a non-constraint problem now, okay? So basically, the advantage of using this one here, you turn that constraint problem into an unconstrained problem. So the question now, why it works? Why is that? Because you see, if I'm looking for mean and max for the L, what would I do? Given this one, what would I do if how do I find, what would be the first step I do to find the mean and max? First derivative test. First derivative test meaning what? Find the critical point. Your mathematical meaning, what do you do? What's zero? Del L. Right? Yeah. You gotta get used to now del L here. So this is basically what you do at here, right? Now del L equal to 0 meaning, what do we do? What are we looking for? Partial L over partial x equal to 0. And partial x equals to partial y equal to 0. And then what? Partial x over partial lambda equal to 0. Right? Yeah. So what would be the first expression? What is the partial derivative of L over x, partial x? Here's a function. Here's a function. What's the partial L over partial x? Partial f over x plus lambda and partial g over x. Right? Second one, partial f over y plus lambda partial g over partial y. The third one, what is the partial L over lambda given this expression? G xy minus c, right? Yeah. So 1, 2, 3. Now guess what? This 3 and this 3 will do the same, right? These are the same thing, right? So that's why this Lagrangian at here is equivalent, okay, statement of the problem, of formulation, given the original problem. Okay? Yeah. Is that clear? Yeah. Okay, so enough of these symbols in here. So let's take a look at an example, okay? Third example here. Let's take a simple one here. Find this mean value of this function subject to the constraint g of xy equal to y minus x equal to 2. Okay. So basically, for this particular one, this is a sort of the graphical representation of what we're looking at here, right? Okay. So you have the function f of x y equals x squared plus y. That's what we call a parabola, right? It's pointing up. It's a bow holding up. Okay. And this y minus x equal to 2. That's a straight line, right, in the xy plane. Okay. So it's like this. So you have somebody here walking along this, maybe this either direction doesn't matter, okay, along this straight line. Then there's another one on the surface, okay, being controlled by the bottom one here. And so you're going to end up with a curve, okay, traced out along this surface. So this is essentially, this is a plane here. It's like a plane, and cutting through this surface, you end up with a parabola, right? A parabola here. So apparently you do have a minimum value, which is somewhere here, right? You do have a minimum value. Okay. Yeah. Later you will know this is a sort of what we call in a quadratic. Okay. It's in a quadratic form. Okay. Quadratic form. And when this is in a quadratic form, this is a quadratic cost function. Okay. Or cost function. So you're guaranteed that you will have a minimum value. Okay? So in the controls, there is so-called linear quadratic regulator, and all they're doing is to minimize a quadratic cost function to end up with suitable control signals, basically. Okay? Yeah. Is that clear? Yeah. Okay. So let's use what we have just did, okay, to derive this, to derive something. Then I'll show you what the two facts that we stated from this example here. Okay? Yeah. Okay. So what do? First step, what I'm going to do is, I'm going to go use the Lagrangian here. I'm going to formulate, okay, form this Lagrangian. Okay. What's the Lagrangian in my case? Lagrangian in my case, f of xy, so x squared plus y squared, and plus Lagrange multiplier times the constraint. The constraint is y minus x minus 2. So now minus 2 actually sometimes doesn't matter, okay? But let's use y minus x minus 2 there. Okay. So, once we have the Lagrangian now, the next step is del L equal to 0. Okay? Yeah, essentially there are three equations, okay, what we need. So, del L equal to 0, what that gives us is, okay, three equations. Okay? So, partial L over partial x. Okay? And what does that give us? 2x minus lambda equal to 0. Instead equal to 0, right? Instead equal to 0. And partial L over partial y, 2y plus lambda equal to 0. Okay. Yeah. Okay. So the last one, partial L over partial lambda, which is what? So three equations, right? Yeah, it's three equations. Okay, so let's solve this one here all together. 2x minus lambda, what does that give us? It gives us lambda equal to 2x, right? So I probably should write this one. This is a sort of the approach you would do, okay? From let's say number 1, number 2, number 3. From number 1, you get lambda equal to 2x. And then we sub into number 2. Okay, sub into number 2. And what do we have? 2y plus 2x equal to 0. Okay? And combine this one with which one? To solve for x and y. What would you do next? Combining this one, this is number 4, with, yeah. Okay? combining these two, solve for x and y, and that's pretty easy. Okay. You can multiply the bottom here with the 2, 4, then add them together. Did I make a mistake? No. Oh, anyway, on my lecture notes is y minus x minus 3, but that's okay. Yeah. We use a 2 here. So what do we get? Y equal to 1, right? Y equal to 1. And if y equal to 1, and what about the x? X is negative 1. Okay? Yeah. Okay? And oftentimes you're probably also interested in the lambda value. So that means lambda equal to negative 2. Right? Okay. Yeah. So those are the solution at here. This is called optimal solution basically. Okay? Yeah, optimal solution, including the lambda. So the lambda is the optimal solution. Okay? So if this is the optimal solution, and you know that it's going to be a minimum, so the next question is, what would be the minimum value, along the curve traced out? So f mean equal to what actually? F is this, right? F is this. So it should be 2. Yeah. Make sense? Yeah. So if you look at the illustration here, it's more or less about right. It's not up to scale. When x, this is x-axis, and this is y-axis. Okay. So you get at negative 1 and 1, and this location 2. Is that good? Good? So what I want you to do is this. You can practice this, okay? Because this is a pretty simple drawing in here. I want you to do this. Can you practice to draw? Can you draw del G? Okay? Draw the del G, and also draw this del F. So basically, draw these two at here. Even use a ruler or something. Okay. What would be the relationship at the mean location? Of course, they're going to be parallel to each other, right? They're going to be parallel. Okay. But it's a good way to reiterate, to reinforce this concept here. As a matter of fact, you see, I draw another circle. So this is the circle basically at this mean location. This is the contour curve for the function f corresponding to this point. Remember the fact I said these two contours should be what? Should be tangent, right? Should be tangent. So it's clearly they are tangent to each other, right? Yeah. Okay, so let's take a look at that example right here. Then we should be able to finish this I can ask you to practice this same function. Now the constraint is this. Okay. Now the constraint is this. Find the mean value. Okay. Find the mean value. I'll give you a couple of minutes here to practice, just to follow exactly the same kind of process that we did it here. Okay, see if you can find the answer. Okay, but I'm going to write down the Lagrange first. three equations. I think they're pretty simple. Should be pretty easy to find out. Three equations. Now you start to solve. Okay. 1, 2, 3. Too long to get an answer. You probably missed the answer, but so anybody able to get an answer? Yes? Okay, so given the time, let's try it here. So this is a typical approach, okay? First is you derive a lambda in terms of x and y, either from number 1 or number 2 equation, doesn't matter, okay? Yeah. And then, as we did in the previous one, we sub this one into number 2, okay? Sub it into number 2. So if we do that, what do we get? We get 2y minus 2x over y, x equal to 0. Okay? So, for this one here, what do we end up with? We end up with what? X squared equal to y squared, right? Okay, that's a dilemma. X squared equal to y squared. What does that mean? That means physically and mathematically means x equal to y or x equal to -1, right? Yeah, that's what it means. However, which one is possible then? Or based on what that we can get rid of one of them? Is this second one possible? And why? Here's a constraint, x, y equal to 3. If you sub this one over here, what do you end up with? You end up with a negative y squared equal to 3. Is that possible? No, right? So this is not possible. So you have to cross it out. Okay? Pardon me? It doesn't matter. You put x equal to negative and then y become positive. Right? So basically due to the constraint. Okay? So this is the only possibility here. Okay? If this is the possible one here, then we can x equal to y here. So sub x equal to y into where? Into equation 3. Okay, so we end up with x squared minus 3 equal to 0. So x equal to positive and negative equal to 3. Okay, so again, here's a tricky number. X equal to positive and negative root 3. So then which means what? For x equal to positive root 3, what is the y value? Y is positive. For x equal to negative root 3, y is negative. So basically, you after this approach here, okay, you end up with two locations. What does the two locations mean? Both locations give us what? A mean value, right? Both locations give a mean value. So now the problem is that possible? Yes, it is. I'll show you an animation here. So both of them give us mean value. So what you need to do is, what is the mean value at this first location? And what is the mean value at this second location? And you will see that they're actually the same thing. Okay? Substitute into it, actually the same thing. Actually, they are all equal to what? What's the function? Function is x squared plus y squared. So when you substitute here, this is equal to 6, right? Yeah. Okay. So I'll show you what this animation here to have a better look at this thing here. Okay. So this is let me see, is that this over here? No, this guy. Here. Yeah. So this is the function x squared plus y squared. Now watch the bottom dot. The bottom dot is x, y equal to 3. So now you probably should consider what is the drawing of x. What is the drawing of x, y equal to 3? It's actually what? Right? That's the drawing of x, y equal to 3. And this is in x, y plane, right? Now imagine, where is the paraboloid in this case? The paraboloid is right on the top of this page, right? Right on the top of the page. If I slice the paraboloid and draw the contour plot, and where will be the contour plot for this x squared plus y squared? What would be that? It would be what? Circle, circle. And there is one particular circle which is going to be tangent to the both curve, and maybe there's another circle here, right? Okay, yeah. So now let's go back to this drawing in here, and you can watch carefully at how you can see what's going on here. Oh, here. So you see this one is not tracing. So right here. What does this tell you at this location? What happened to the blue color and the red color? Basically they are two tangent vectors. They become parallel. That means that must be a mean location, right? So maybe the next one is better. The next one trace out this. So. See that? Zoom in here. Anyway, so you see the variation of this, right? So I'm going to upload this one here. You can find a computer anywhere on the campus. You can play around this thing here, and then basically you get some idea, right? Yeah. Okay. So that's basically what I'm going to cover for Lagrange multiplier. And then there's some optional stuff in the lecture notes, so you can take a look at it. Basically, your constraint may not be just one. You probably will have two constraints, right? So then what do we do? Okay. So you're actually going to, the Lagrange multiplier basically will become a vector. Okay? Yeah. So I'll just make use of the rest of the time, just quickly mention the midterm here. Don't have much time. Let's say something.